Hello students. So coming to the second part of mechanical properties of solids. So we will study here about Hooke's law, the stress and strain curve, and the Young's modulus. So different types of elasticity or different types of longitudinal strain and the shearing strain. Let us go with the Hooke's law first. Hooke's law. Statement I will read out. Within the elastic limit, the stress and strain are proportional to each other. So, the Hooke's law states that for any substance, the stress, when you are applying some stress to a substance, there is equal amount of strain produced in that substance. Okay. This statement is known as the Hooke's law, and it is fundamental law in elasticity. It is the fundamental, that is, it is valid for all the substances. That is, when we apply some stress, there is equal amount of strain in the substance. Okay, and we can write this proportionality constant as a constant value k, and this k is nothing but the modulus of elasticity. So means what is the modulus means? It is the ratio. Modulus means ratio, because now if we want the value of k, k is nothing but stress upon strain, stress by strain. So this is the modulus of elasticity of a particular substance. So within the elastic limit of a substance, so when you are applying when there is elastic limit in the substance, still it has not lost the elastic property of the substance, then whenever you are applying stress to a body, there will be proportionality of strain. Okay, so this is known as the Hooke's law. Now let us go to the stress and strain curve. So I will show you the diagram. This is the stress and strain curve. In the diagram you can see, so there are different points. So along x-axis there is a strain, and along y-axis there is stress. Okay, so whenever we are applying the stress, there is change in the strain. So let us see the curve here, that is stress and strain curve. Very important it is. It will be asked for 3 marks. The relation between stress and strain for a given material under tensile stress can be found experimentally. The applied force or load on the wire is increased in steps. So when there is, for example, if we take a wire and if you apply some load to the wire, there is stretching. So originally it will be the length of the wire will be L, and when you are applying some stress to it, there will be extension in the length of about L plus delta L. Okay, so it will be increased. Then in the figure you can see O to A is the curve, and it is linear. This region obeys Hooke's law. So in the initial part, that is from O to A, as you are applying the stress, there is equal amount. So if you take this part of the stress, so when you go along the x-axis, there is equal amount of strain in the wire. So this from O to A, it is known as the proportionality curve. It is known as the proportionality curve. That means if you remove the stress also, and the wire will come back to its original shape, or the substance will come back to its original shape. Okay, now the region from A to B, this region, little bit it is not proportional, because there is the curve has changed now. It is not a straight line. So from A to B, it is not a proportionality. It doesn't obey Hooke's law. Okay. Now, and the point B is called the yield point. This point is called as the yield point or the elastic limit. The corresponding stress is known as the yield strength. This is known as the yield point. The point is known as the yield point, and the strength is known as the yield strength. If the wire is further loaded, if the wire is further loaded, the stress developed exceeds yield strength and strain increases rapidly even for the small increase. So now it has lost its, now from B to C you can see it cannot come back to its original shape. Okay. So even for small increase it has lost its elasticity, and again if you increase the it will come to from C to D. It is a permanent set. Completely it has lost the elastic property. So now at this point the body does not regain its original dimension. This is called the permanent set. So as I told you, from C to D it is the permanent set, because even after removing the stress the body does not come back to its original shape. This is called as the ultimate strength. So this is known as the ultimate strength. That is the sigma is known as U is known as the ultimate strength. Sigma U. Further increase in the stress and the point E is reached. That means the wire gains a fracture point. That means that if you are increasing the stress more and more after D point also, ultimate strength also, that means it is the last strength of that wire, and if you put still more little bit more stress on the wire will break. So that point is known as the fracture point. Further increase in the stress at point E, the wire gets a fracture point or it breaks. So this is known as the stress and strain curve. From O to A is a proportionality curve. From O to A is proportionality curve. That means it obeys Hooke's law. From A to B, little bit it has extended. It does not obey Hooke's law. From B to C, it is still more stretched. From C to D, it is a permanent set. It will do not come back to its original shape. It has lost its shape, and still more further increase in the that is sigma U is the ultimate strength of the wire. Still more increase in the stress will break the wire. This is known as the it reaches a point E, and it is known as a fracture point. Now let us go to the elastic moduli. The ratio of stress to strain is called the modulus of elasticity. There are three types of moduli of elasticity. So I told you the ratio. Moduli means the ratio. So if it is stress to strain ratio of elasticity, how many types there are? There are three types of modulus of elasticity. One is the Young's modulus, second is the bulk modulus, and the third one is the shear modulus. Let us see first the Young's modulus, and it is denoted by the capital letter Y. It has been given after a scientist named Young, and it is denoted by Y. The ratio of longitudinal stress, that is it may be tensile or compressive, to the longitudinal strain is called Young's modulus. It is denoted by the symbol Y. Consider a wire of length L and area cross-section area A suspended from a rigid support. Let delta L be the increase in the length of the wire due to load F applied to other end of the wire. F is proportional to the area A of the end face of the wire. So longitudinal stress is given by, it is denoted by sigma F upon A, force by area, and strain is given by epsilon equal to delta L by L. So it is longitudinal strain delta L by L. Young's modulus is ratio of these two, that is longitudinal stress by longitudinal strain, FA by delta L upon L. So it will be FA into, so this denominator L comes in the numerator, L upon delta L. This is known as the Young's modulus. Its unit is Newton meter, and its dimensional formula is m L raised to minus 1 T raised to minus 2. So we will see this experimentally also. So always Young's modulus will be in lengthwise, that is the stretching of the wire. So taking the example of the stretching of the wire, the Young's modulus will be explained. Now I told you it is a experimental arrangement. You can see in this diagram there are two wires, so I will explain you the determination of Young's modulus of the material of a wire. A typical arrangement of the to determine the Young's modulus of the material of the wire under tension is shown in the figure. It consists of two wires A and B of the same length and radius of same radius. Both the wires, that is the reference wire, this is known as A is the reference wire and B is the experimental wire. They are suspended from a rigid support. Okay, so this one A is the reference wire where it is connected to a vernier caliper, both, and the scale is connected to the wire B, experimental wire. So in reference wire the load is constant, but in experimental wire we will increase the load. On the wire, one wire is reference wire and the another wire is experimental wire. They are connected by a vernier scale. When we apply load on the experimental wire, there is extension created in tension created in the experimental wire. So when you are applying some load to it, there will be tension created by the wire. Tension is given by T is equal to M into G. So tension is nothing but the force. F is equal to M into G. Right? So that's why. So what we will do, first we will take the area of the wire. A equal to pi r square, F is equal to M into G. So now as we have seen in the previous slide, Y equal to F A upon L upon delta L. Then F is nothing but here M into G. L upon A is what? Pi r square into delta L. So this is the formula for the Young's modulus and this is the exponent. So Y is equal to F upon pi r square L upon delta L. By knowing this one, the force we can calculate for a particular mass, M into G. Okay, R is taken as the radius of the wire, so we can get this term, and L is the original length that can be seen, and delta L is by taking number of readings for a particular, for each mass we can get delta L also. So this is how the Young's modulus of a wire is measured experimentally. Yes, let us go to the next slide. Shear modulus. So what is shear modulus? Shear modulus is nothing but at an angle the body will be tilted at an angle of theta. So that is known as a shear modulus. The ratio of the tangential stress to the shearing strain is called the shear modulus or modulus of rigidity of the material. It is represented by the symbol eta, and we have tangential stress sigma equal to F upon A and shearing strain theta equal to delta L upon L. So now Shear modulus is the ratio of these two. Eta is equal to sigma upon theta, that is F upon A. Again it will get the Young's modulus, same, Fa into L upon delta L. So shear modulus is eta is equal to Y by 3. It is 1 upon 3 times of the Young's modulus for a given most of the material. So shear modulus of a material is less than the Young's modulus. So let us go to the bulk modulus. Bulk is nothing but the volume. So let us see what is bulk modulus. The ratio of the hydraulic stress to volume strain, or we can also say volume stress to volume strain, is known as the bulk modulus. Understood? Now, consider a spherical body of volume V and surface area A. Let F be the force of compression from all sides normal to the surface. So this is the spherical body and we are applying the force on all sides to the body in this manner. The force is taken as F. Now the force is the bulk stress. Okay, it is the bulk stress, that is force upon area, and if the body is compressed inside, so there is change in the volume delta V. There will be change in the volume delta V. So this is known as the volume strain. So that is, it is what is bulk modulus? It is hydraulic or volume stress divided by volume strain. So B is equal to F upon A divided by delta V by V. So that is F by A into V by delta V. So this is the bulk modulus. If the spherical body is compressed due to hydrostatic pressure P inside a liquid, then for liquid specially we take it as, so pressure is again, pressure is what? Force upon area. Now if we take in terms of liquid and it is compressed inside, then we will take it as negative. So negative sign indicates that when pressure P increases on the volume, on the substance, the volume decreases. So P is positive and delta V is negative. So SI unit of bulk modulus is same as that of the Young's modulus. The reciprocal of bulk modulus is called as the compressibility, denoted as K. Thank you for watching.